Hello again, it's Phil Story, and today we're looking at NetData's Waterfall chart. It's a very useful chart for looking at transactions in groups and also for measuring performance of user function being a group of transactions that perform a particular function for a user. In terms of all the NetData charts, the Waterfall chart is a subset of the timing chart. We're going to be using our usual display controls. Because we need transactions, I'm going to use Kerry's PacketBomb Slow Web PCAP that we've used before. We want to look at transactions, so we're going to start with the performance chart. We just jump straight to the performance chart. Here are all the transactions, and what we need to demonstrate the waterfall chart is to choose a set of transactions that we can look at as a group. So if I just zoom in and find a nice sample of transactions, let's see how this looks. We press the timing button to get to the packet timing chart. Yes, we do want to load packets. If we load packets, we get extra information on the waterfall chart. Here's the packet timing chart. We know there's only one client, but we also know that there's lots of different servers. There's a few hundred TCP connections on the page, and the next thing we want to do, format, pick waterfall in this tab. And there we see our first look at the waterfall chart, and it's displaying individual transactions. And luckily, they're all fitting on the one page. If we had too many, we would tick here, allow multiple pages, and that will give us a scroll bar that we can scroll up and down. So while I'm here, I'll mention these different radio buttons do different kinds of plot. Transaction types will put transactions of the same type on the row together. Unique transactions, in this case, is very similar to individual, but that's useful for being able to spot easily the same transaction that's repeated over and over, because repeated transactions will appear on the same row. And then categories will really squash it up, because in fact everything we've got here is a get. So it's essentially NetData has made some decision to group various gets together on the same row. Now the key attribute of the waterfall chart is in fact we have a waterfall of transactions as they occurred, and we can see the timing breakup of the transactions based on the colors. So yellow is server time and blue is network delivery time. And so the ones with large blue times, there's 115K from the server, and that took 290 milliseconds. But the server thought about delivering that answer for 155 milliseconds. So we get a big visual cue on the chart of which colors are responsible for most of the performance of this set of transactions. And there's a summary in the top that is adding that up for us. So we sell here 60% of the time for this set of transactions was server time, and 40% was delivery of the packets across the network. Now in the top right corner is, and you need to load packets to get this information, but it's a little table breaking down how many round trips were involved in this time period. But it's not the total round trip, because we can see down the bottom right here, as usual with NetData, there's the count of things on the page. So on this page right now, there are 70 transactions on 71 connects. So with 70 transactions, you would think that that was 70 round trip, but NetData in the corner here is saying 42.3 round trips. And that's because NetData has calculated a critical path through these transactions, and in that way is not counting round trips that occurred in parallel. The critical path is indicated by the blue lines that surround the transaction. So that's surrounded by blue, and then the next one is this one, and then that one, and a little bit of that one, and as you can see. So not every transaction is included in the round trip count, and there would be multiple round trips involved in delivering these large blocks of data. All up, there were 42 round trips that the user would have felt in loading all these transactions. Now, format, we come back to the format control window, and here we can model the effect of an alternate loop delay. So if we tick this box, we'll get a box over here where we can tell that there are 5 different servers involved in this, and we could type in here a different round trip time for each. And we might do that if we were moving some of our servers to, say, an Amazon cloud, and we were moving some of our servers to another data center. But just for the purpose of today, let's just say we're going to make every server 20 milliseconds away and replot. Now what NetData has done in our table in the top corner is said, okay, we had 42 loop. It was a 1.2 second function in the first place. We're going to add another 0.84 seconds of round trip time because of the 20 milliseconds, and that will turn our whole function into 2.1 seconds. In other words, a 66% increase. So using NetData and the waterfall chart in this way, we can model what will happen to various user functions if we're going to move servers between data centers or into the cloud. I'll turn off that part. As well as a little text block in the top corner with the round trip calculations, there's also a further break up of where the round trips occurred in this little legend box as well. And it's basically telling us how many round trips in this particular critical path in the server time or in the message delivery time. One more thing we can do here, let's suppose we decide that this one, which is in the critical path, we don't want it in the critical path, we can right click and say classify and exclude from summary. Now if we do that, you'll see that the blue line, or the critical path, is now shifted, and we've actually come down to 61 loops now. So this one large transaction is now in the critical path, and it's taken all of these ones below out of the critical path, and we've actually dropped down to 61 loops. But there are 39 round trips involved in delivering the 161K. We decide, no, we didn't want to do that. Right click, allow, and NetData will recalculate back again. In the link below the video, you'll find a URL to get the PDF with this paper that I wrote recently about predicting application performance before moving to the cloud or moving data centers. And in this paper, I basically document a procedure that we used back in 2009 to analyze some of our applications before we move the servers. You can get the report and read it. I don't want to discuss the report too much here, but I'll use it as an example to show what some of the groups of transactions we did, or what some of the user functions were, and how we analysed them back then. And this paper also serves to describe to you how to interpret the waterfall chart. And I have these various PowerPoint or call out to help you with that. We start with a fairly simple one, and again we in the top right corner, this one was only 24 round trips in total, and in all of these examples we made the servers 15 milliseconds further away than they were, and we get the outcome here. Even this small one, it would go from a quarter second to essentially a half a second. We could probably live with that. Now this one is purely an Oracle application, but you see the large amounts of blue is because we did 27 SQL queries that returned 890K. So in this instance, there's enough round trips to make the whole transaction 5 times longer, but because there's a lot of network delivery time, when we're moving this server, we also need to make sure that we're provisioning the network to cater for it. Here's a particularly bad example of an Oracle application, and it retrieved 20,000 rows, one row at a time. So it does a SQL query that says, give me the first row, and then goes back and says, give me the next row, give me the next row, give me the next row, and it does that 20,781 times. Each one of those is a round trip. Therefore, in the table here, we see that this originally 33-second transaction would turn into a 6-minute transaction. So now that we know that we can't really move this one without doing something, but we know why. It's these one-row SQL queries. So the fix would be to change the application so that it retrieved thousands of rows in one go instead of one. The other interesting thing on this chart is the grey time here, which is client reaction time. 40% of this whole period is client time, and client time is the time when there's actually no network activity. And since we can't see any kind of white space between these blue vertical lines, the interpretation is that the application, it fetched a row, then spent a little bit of time processing that row before it asked for the next one. The sum of all those little gap between each of these fetches adds up to 40% of the whole time period. This is an example of an application where you really do need to go and talk to the developer and get that application changed. This one is very similar, except this is 2600 SMB reads returning 26 meg. So it's returning about 10K per read, and it's doing 2600 of them. As before, there's a lot of client time in this, but in this case we can see the client time. It's this white space here where nothing was happening. This is another Oracle application. In this case, we're fetching rows 100 at a time. We did 132 of those fetches, and in fact this time the time is blue. Or in fact, because there's 132, some of the fetches took a long time, and some of the ones in between were very quick. No matter what, the total time, or the vast majority of this time, 95% of the time for this function is network delivery time. So in this case, we may not be worried about the round trips, which add 20% to our time, but we might be worried about provisioning the network to make sure that it can handle this properly for the right amount of users. This is just to show a different mix. There's SQL and there's this image servers. 1.3 seconds turning into 2 seconds, we could probably live with that. I included this one just because it just can show that NetData can do the various protocols, but including Telnet. So this row here is 95, 3270 mainframe screen scraping tasks. So this application, as well as some database activity and some image activity, had some screen scraping to a mainframe. But in this case, we can see there is actually a lot of white space where nothing's happening. It's showing up as 90% client time. So 90% of the time spent for this whole function is in fact the PC itself doing process, and an extra 4.5% of round trip time for a 795 second function. Presumably this would be a printing of a report. We could probably live with that. Lastly, I included this one because this is an example taken from the PCAP file that we looked at with the live app at the start of the video, and I included this to point out which items in the format control window likely to be interested in, and to not be scared off by the packet timing chart that looks quite complicated at the beginning. So that's a look at the waterfall chart and some of the controls. In the next video, I plan to do a real-life case study of where the waterfall chart played an important part in solving the problem.